Okay, let's get started. My name is Andrei Kohan. I'm Networking Solution Architect at PLVision. And today we are going to talk about something very important, about quality. So as you can see, our topic is about SONiC-based test framework for SAI testing. But in fact, it's not just about testing. It's about prototyping. It's about debugging on SAI level. So PLVision, as a networking software development company that is located in Poland and Ukraine, provides, I would say, premium level of technical support and collaboration, starting from idea and all the way up to the final solution with quality in mind. Even we officially joined the OCP community just recently, we are contributing to such type of project as SAI and SONiC from early days, usually on behalf of our partners, switching silicon vendors. So in today's networking disaggregation world, we see many benefits because of this openness, because of specifications are available, free access to the sources, freedom of choice of component or the final solution. But in fact, for the end customers, the freedom is not free. So it's still sometimes not clear what is the release cycle, who, when, and how tests this solution, and how to add new components, how to upgrade components. And one of such crucial components is SAI, which is basically the contract between ASIC vendors and applications and community. And usually we test SAI with so-called Schrift-based interface, where the Schrift server becomes as a driver for SAI library. We link Schrift server together with SAI library. Then have this interface, the client part that exposes some kind of Python interface. And you know, it works pretty well on API level. The question is whether we can do something more, whether we can do it even more efficient on application level. To answer this question, I propose to take a look at high-level architecture of SONiC. I believe you saw this, such type of pictures today probably a few times. Here we group the functionality or the building blocks of the SONiC into two major parts. The top-level part we called SIC NOS. The major business logic is there, the networking application that writes the information into the AppDB, then our agent that takes the configuration and convert it into SAI format and put it into the ASIC DB. And then everything below, we can call it SYN-NOS, or let's call it SONiC Lite. Because with those bottom part, we still can run SAI, we still can configure ASIC, and we still can benefit from this solution. And do you know what type of interface is between our agent and ASIC DB? So in fact, it's networking connection. In SONiC, it works through the loopback interface, but in fact, we can expose it to be available from remote access. From SONiC platform perspective, everything is the same, especially the top part. So the same applications, same database. The difference is in the bottom part. Even we still use the same syncd sources, we have separate Docker environment for each ASIC vendor with pre-installed dependencies needed by the SDK. And how this communication is happening between our agent and syncd? It's not something our agent just put the configuration into the database and that's it. In fact, our agent and syncd uses Redis database as a producer-consumer approach to send the data through the queue. So as you know, in SONiC, you have 3 modes of operation for this communication. It's asynchronous, synchronous, and zero-message queue. And synchronous mode of operation is most commonly used. It means when you send the configuration, or agent when send the configuration, syncd should respond with the status code. So in this case, syncd is a driver for SAI library. SAI Challenger utilizes this approach, this feature of the SONiC. We keep all bottom part of the SONiC as is. So it's Docker environment with syncd inside. The only probably difference is in SONiC, syncd is a separate Docker, Redis is a separate Docker. We usually pack it into one Docker container. And SAI Challenger provides a simple Python API to communicate to the Redis as a node-bound interface for the final solution. So still the same syncd sources as we have in production. For implementing test cases and running them, we use PyTest, which is used actively in SONiC community instead of PTF test cases. But we still, at this point, use some PTF utilities to send and receive packets. So I often hear the question about hardware traffic generators. And yes, I see many use cases when this can be beneficial. And that's something that is really in our backlog. So that's something that we are considering to add to get this benefit. So from use cases perspective, as I mentioned, SAI Challenger is not just test framework. In fact, it provides the possibility to develop new features. So we can consider the bottom part of SAI Challenger as a SDN-like approach to expose the interface through the network and get this configuration remotely. Of course, we can do SAI testing. In fact, it's not just testing, it's testing and integration in one shot, because you need to build your SAI library as a Debian package. And when you compile this Docker image for SAI Challenger, basically you validate that it will work the same way for SONiC final solution. And of course, debugging. By debugging, we mean a few things that we already added into the SAI Challenger. First of all, as you know, SONiC produces so-called SAI Redis record file, which is the configuration that our agent push through the Redis to the syncd. So this is stored in way of strings. And SAI Challenger already has the functionality to parse these record files and use each record file as a separate use case. So we can get the record files from end customers and use these files in our CI/CD process to make sure we do not break the design of our customers. Also, since we utilize this Redis database as an interface, just with 200 lines of Python code, we provided a simple CLI. It's click-based. Actually, the same that is currently used in SONiC. So you can configure SAI manually. This is very useful when we have some test case, we put the breakpoint, run to those parts, get this configuration, and then go and check the configuration manually. So as you can see, the idea around SAI Challenger is to, first of all, reuse as much as possible of existing SONiC components, because we assume that they are expected to be production quality, right? And you may ask what happens if we found some issue in syncd that happens. Then I believe we should pay back to SONiC community and go and fix it there. Another question that I often hear, SONiC still does not use all possible SAI APIs and attributes. What if you want to check that? But if you explore the sources of syncd, it actually implemented in the way that it covers most of the functionality available in SAI nowadays. So SONiC just use what it needs for that. but again, we can use more, or we can extend if needed, right? From operational mode of perspective, we support 2 modes as of now. As you may guess from the picture, standalone mode is a single Docker image with everything inside. This image can be installed, let's say, to ONL-based environment, and you will have everything you need inside. But in this case, you will not be able to run packets. So you can run just some SAI configuration, and that's it. Also, as you know, SONiC contains so-called SAI-based library, which is stubs for SAI library. But again, this can be used for prototyping, for test cases development, without packets. So you can just download the sources of SAI Challenger, build the Docker image, and by the way, it takes just up to 10 minutes to build the image and get everything you need. And you can start your activities right away, even without access to real hardware. Client-server mode is the mode of operation that should be used in case we want not just configuration, but also to run some packets. In this case, server part, it's very similar to what is in standalone mode of operation. We build single Docker image, install it to the target device. And client part contains just test cases and provide just those simple communication channel to the server part. However, client-server mode can be used for all cases available in standalone mode of operation. So it's up to your choice. Here I also need to mention that the third mode of operation is also possible. As you can see, the major part of this environment is based on existing SONiC components. So with some small changes in some configuration files in SONiC, we can run SAI test cases with 0 changes on the target device. So you can have in production your target device, stop services that you don't need, and then run these test cases or some your specific use cases or scenarios. Here you can see the example of high-level architecture of this solution. It's basically the part that provides the API, the interface for the configuration. It consists of 3 layers. The top one, which is SAI, it provides a very basic generic API, very simple, create, remove, set attribute, get attribute. That's it. A few additional APIs that can be used. You can see the redis apply rec, sorry. As you probably guess, this API we used to play those SAI redis record files. The second layer of abstraction is switch type abstraction. As you probably know, in SAI recently another type of switch object was added. It's PHY device. There are a few others there. At this point, we are considering to add the support for 2 types of devices. It's NPU device, switch in silicon, right? And PHY device. You can see some APIs defined for SAI NPU device. SAI PHY support is still in progress. They are specific to switch in silicon. You can see bulk API, bulk APIs and some APIs to get and clear the statistic, or FDB-related API, which is not related to PHY itself, right? And the last layer is vendor-specific. It's implemented in the way of plugins. So if you need some specific configuration to be applied before you run the test cases, with just few lines of code, you can add those specific configuration. Let's say you have some specific hardware table where you need to have a default entry to make it work. So you can do it. If you do not need some specific configuration, you can just go ahead and use SAI NPU abstraction. From testing perspective, we propose 3 types of testing. It's unit testing. Here, by unit testing, we mean run test cases without traffic. you can do at attribute level get, set, get operations very efficiently. I will show in a minute. And also functional testing. It's more closest to what is currently available in PTF environment, where you create simple L2, L3 scenarios. In this case, you can run packets, but we usually add additional validation when you can switch off the packets generation in case you run in standalone mode. And the last mode of operation is integration mode of operation. Here we assume applying those SAI Redis record files. And also I will show in a minute how the test case looks like. So as you can see, for unit testing, the approach is very simple. So you can just open the header files for specific SAI feature, take the attributes from those header files, and create the table that you can see on your screen. Attribute name, type of the attribute, value that you expect to get when you make a get operation. And with just 2 lines of Python code, you can validate all those attributes. And you can basically do the same for set operation or make some kind of scaling testing on negative scenarios. That works pretty well. From functional level perspective, in this example, you can see how we create, let's say, VLAN member. We just use create API, which is generic for all types of SAI objects. You provide the type of objects that you are going to create. You provide the list of attributes, the values for those attributes, and here you are. So you don't need to remember the API for each separate SAI object. You can very easily understand what you configure just opening your test case. Because, as you can see, the name of the attributes is exactly the same that you can find in SAI headers. Then we send and validate some packet and remove the object by generic API, which is remove, which takes object ID that we are going to remove. There are special cases, separate cases for the objects that are not object ID based, but like route or FDB. But the same API can be used. It detects whether you provided object ID or structures that define your entry. Integrational testing, just list of SAI Redis record files that you want to apply in your solution. And again, 1 line of code. And here you can see the example how we run these scenarios for some Broadcom device. And of course, here we can, if needed, we can add some additional logic to send and receive packets when we apply those configurations. Or you can do it just manually. As I mentioned before, we have simple CLI. Here on the screen, you can see the very simple example how we create switch with some specific attributes, retrieve the list of ports, and then check the operational state of some specific port, and then retrieve the counters and clear them. As I mentioned, this simple CLI is very useful when you are debugging something. Since we are providing this solution based on PyTest, there are a number of different plugins that you can use. And you can get the results in different formats. Here is a simple example with all useful information for you. So it's flexible. And finally, similar approach can be used not just for NPU testing, but for PHY testing. Why is that? Because in SONiC, as you know, PHY is just other type of switch object with own syncd. So the approach here is very similar. So in fact, you can implement a simple PyTest fixture and add it on top of your existing test cases and test all together your ASIC switching silicon and your external PHY device. I believe the same approach can be used, let's say, in Dash project when you run the solution on top of SmartNICs, because it's lightweight, it's simple to bring up. So, as I mentioned, that's something that is still in the process of implementation. And finally, we come to the call for action. As of now, this solution is located at PLVision GitHub, so all sources are available. You can go and download and try to play with it, just 10 minutes, and you can experiment with it. Instructions are available there as well. So we expect some additional contribution, probably around some ideas, how to use it, propose new use cases, propose new kind of topologies. I want to mention that SAI Challenger provides the way to apply the configuration. In SONiC, we have T0, T1 topology, which is basically basic configuration. SAI Challenger proposes the approach to do similar. So you can define the basic configuration and then reuse it in your test cases. So new topologies are welcome, extension of the core functionality. And again, we are currently under a negotiation with OCP. We are planning, we are ready, we are open to contribute this solution to the OCP GitHub. That's probably it. Questions?
This is very useful for existing implementations which have already integrated with SYNC-T. So if I'm developing a new API, I would not have anything integrated with SYNC-T. So how are we going to test in that case?
That's a very good question. So I will answer to the different questions first. What I will choose if we have this PTF solution and SAI Challenger. It's not instead of, so it's not something you should choose one of that. I would say it's slightly different level of testing. So in case you implemented just few APIs, I would still suggest you to go with the PTF approach through the Swift interface for those specific APIs. But by end of days, you come to the funnel solution and you need to integrate and you need to have simple way for prototyping. As I mentioned, it's not just test environment. It's for prototyping, for debugging. So that's how I see it. Okay. If no other questions, thank you very much for coming. Thank you for joining.